What's on the docket for today? I have markers. I want to go over this little handout here just very quickly. I want to talk about a new statistical technique, and sort of prepare for the end of the semester, figure out what to end up with. So, as you know, last time we did principal components analysis, and presumably you've had some luck doing that in the past. I know some of you have. It is much easier and it's a much more pleasant environment to do it in Program Pass than it is to do that in R. I have been, over the last couple of weeks, banging my head against the wall with R, attempting to figure out how to do time series and so on. And I'm finally 99% there. I have that last percent to navigate. And that's primarily an interpretation step. And what I'd like to do is show you two routines here. The first is, let's see, make sure. Yes, the first is just a stepwise regression, and that's something that we've already done in R. And I want to show you how it looks when you do it in SAS, and it's a much more pleasing sort of result in SAS. And I say that because you guys are going to be here for another year or two, some of you at any rate. And if you use SAS, it's just, your life is so much easier than using R. The nice thing about R is that it's free. The bad thing about it is that it isn't a very user-friendly interface. So I want to talk about stepwise multiple regression in SAS, and then I want to talk about the both piecewise and autocorrelated regression in SAS. I will put up the video with the autocorrelation stuff using R. I'll put that up sometime this week. And then the plan is for today, the other thing that I want to talk about, canonical discriminant functions analysis, which is sort of a different ball of wax. So today, first thing is review stepwise regression. Second thing is going to be splines and autocorrelation. And then we're going to finish up with canonical discriminant. Okay? I don't like that marker. All right, so let's begin by looking at this first printout. The way SAS works is the command, the JCL, the job control language, is archaic in that it goes back to the days when your computer code was on cards. You guys probably don't remember this, but years and years and years ago, you used to get your bill from the utility company. It was on a thin cardboard-like card, and it would have all these holes punched into it. If you're a graduate student, you could get a job as a key punch operator, and you could go work for some company typing on this little sort of typewriter machine that will punch the holes out of those cards. So all of your computer core code went onto those cards. And then, when you wanted to execute your program, you'd take your box of cards and walk it over to Academic Hall, and they had a card reader. And you would stack your cards in the card reader and hit the button, and it would read all of those cards. And then, the job would be transmitted to the mainframe computer, which occupied the basement of Academic Hall. So there's this huge room 3 times the size of this one, just filled with computers and tape drives and all of that sort of stuff. That was the mainframe. And then it would execute the program, and your job would come back on a piece of perforated paper. Many, many, many sheets of perforated paper that were all attached together. That's why when you look here, the job control language has been simplified. You no longer have all the stuff that tells the mainframe where to find the program, what to do with it, all that sort of stuff. You just begin the job with data. And then you have to tell the input statement is what are the variables that this thing is going to read, and then you put any new variables that you're creating, multiplying variables times one another, taking the log, that sort of stuff. And at the bottom you have that statement that says cards. Every command in SAS ends with a semicolon. Then comes all of the data. And we're not going to go through all of this stuff now. And on the back page, on the back of that first page, there's the program. So it says proc, which stands for procedure, stepwise. So I'm telling SAS that I wanted to do a stepwise multiple regression problem. And the model, the next statement is model, species equals, and then I have this long list of variables that I wanted to consider when it does this stepwise regression. At the very end, I put a backward slash, and then I say, use the stepwise procedure. So I know I said proc stepwise, but remember there are a bunch of different ways to do the stepwise procedure. Max R-square improvement, minimum R-square improvement, backward selection, forward selection. The stepwise default routine is one in which it's evaluating both forward and backward selection. And then I just had a little command that says run. And now turn to the next page and you see what it looks like. We're just going to look at a couple of these. The very first step that it has, okay, it says, it gives you the ANOVA table. And remember, this is for that data set in which I had 20 observations, right? 20 field sites. And I'm trying to build the most parsimonious model possible. The model statement, right, has 1 degree of freedom, error, 18 error degrees of freedom. The model is significant. Notice at the top it says R squared equals 0.41. So that first variable that's entered explains 41% of the variability in the species variable. It's unable to compute Mallow's P for me for some reason. I don't understand why in this execution it didn't work. But right below that upper part, it gives you the second, it gives you the model that it's produced. The intercept is minus 1.04, and the slope is 0.12. So that's associated with January temperature. In other words, the warmer it is in January, the more lizard species you're going to get. So it then goes through a bunch of other steps. We're going to skip through all of those things. Skip through all of those, skip through all of those. It ends up, go to page 5, it ends up producing this model that has 3 variables in it. January temperature, July temperature, and warm season precipitation. Okay? And my R square for that particular model is 76%. If you think back to what we did in R, that's essentially what we got in R. Those 3 variables, January temperature, July temperature, and warm season precipitation. Below that, it gives you a summary of the steps, and it shows you exactly what was entered, what was removed, in which step, what the model R square is, what the partial R square is, and all of that sort of stuff. Okay? So this is a much more user-friendly sort of way to approach it. All right. But we did get essentially the same result we got in R, which is reassuring. Okay? So if you're stuck, you don't have access to the university computer system, you don't have access to SAS, you can still do it in R. The next program is this one that we're looking at. The inputs are close, day, and then an indicator variable for president. Okay? So this is the close of the stock market on a particular day. So the days start here with day 3,000, and the stock market was 828.96 points. Okay? Anybody know what the stock market is at now?
Very good.
Yeah, but what ballpark, what the value is?
Oh, I have no idea.
It's just banging on the door for 30,000. So from 898 points to 30,000 points. Okay, so the stock market has done well. I think this precedent right here is for Ronald Reagan. Notice what I do on that input statement. So this is the same thing you need to do as you do your spline. Day P equals day minus 33,988. What is 33,988? That's the point at which we're switching from Reagan, Bush over to, who was the next president after Reagan, Bush? Test your knowledge of history. Who came after Herbert W. Walker Bush? Oh, come on, you guys. Think. Who was it? Who was the president after Reagan? Uncle Bill.
Yeah.
Clinton. Okay. So here we're comparing Bush, Reagan and Bush, right? Reagan, 4 years of Reagan, another 4 years of Reagan, 4 years of H.W. Bush, and then the transition to Clinton. So that number, 33,988, is the day when we make the switch from Clinton, or from Bush to Clinton, okay? So now look at the commands down below. The first thing I'm doing is I'm defining a new data set. The first data set is called Reagan. Notice the very first day of that code, and I've not given you all the observations here, and you can see that there's a big gap. I go from day 865 to day 3251 because I didn't want to have hundreds of pages of data here. But at any rate, notice what I'm doing. If you look at the very first line, it says data old. So I'm telling SAS I'm building a data set and I want to call the data set old. So data old semicolon. Now look at at the end of this program it says data Reagan semicolon. I want it to take the data set old, and if the indicator variable called president is equal to 0, I'm going to put that observation in this data set called Reagan. I'm building another data set called Clinton. I'm using data old. And if the value of president is equal to 1, I want to include that observation into this data set called Clinton. And now I do something called auto-regression. And so I'm doing proc auto-reg, data equals Reagan. Model is close equals day. So I'm looking at the value of the stock market. I'm regressing that against day. But it's an autoregressive procedure. That is, what I'm doing is I'm looking at the residuals, the error terms, and I'm regressing them against one another. And the regressions are, I have an n lag equals 30. So I'm looking at the correlation between today's value and yesterday's value. That's a lag of 1. And I'm looking at the correlation between today's value and the value 2 days ago. That's a lag of 2. And I keep doing that until I go today's value and the value from 30 days ago. And I'm assuming that by the time I'm 30 days out, the value of the Dow Jones is independent. Okay? And I do that procedure twice, once for the Reagan data and once for the Clinton data. Let's look at the results. And the reason I want to show you this result is because of something I want to draw your attention to when you do this in R. So notice the very first thing I get, this ordinary least squares estimate. I get sum of squares errors, mean square error, and all that sort of stuff. It also gives me the Durbin-Watson statistic. So there it says, and you can get that in R. All you have to do to get it in R, depending on which package you're loading in R, I'm loading the package that I'm showing you to load. The command is going to be dw test. So dw test paren, and then the name of your model. And it'll give you the Durbin-Watson statistic. But in this case, this first initial analysis, that is where I'm just looking at the close against day, the Durbin-Watson statistic is 0.01. It's almost 0. All right? That's not good. If the value is 0, right, that means I've got strong, significant autocorrelation. I want that value to be up around 2. Okay? And it gives me my model. So this is for the Reagan data. And notice what happens to the model. The intercept is minus 18,747. And the Dow increased by 0.6494 points every day. That was significant. Okay? So under the Clinton-Bush years, the value of the Dow increased by almost 1 point every day. But now look at the table below that. And this is the table of the autocorrelations between the error terms. And on the right, you can see the value. And notice when you have a lag of 0, the autocorrelation is 1. Well, duh. Your value today is perfectly correlated with your value today. Okay? But at a lag of 1 day ago, it isn't quite 1. And notice what happens to that as we drop down. By the time we get down to day 26, the lag is about 0.8. And let's see how far I go with this. I only go down to day 30, and the lag drops down to 0.77. So if I want to get to 0 autocorrelation, I'm probably going to have to go out 3 months, okay, rather than just 1 month. But now, let's look at what happens when we take those lags out, remove them from the model. Notice what happens to the Durbin-Watson statistic. So that's on page 18. Now, my Durbin-Watson statistic is 1.9957. It's almost perfectly 2, which means that by the time I've removed all of those autocorrelations, I now have an uncorrelated model. Okay? The autocorrelations are functionally gone. And notice what happens to the value of my relationship between the close of the stock market and day. My slope is now 0.6378. What was it before? Initially, it was 0.6494. So once you correct for the autocorrelations, the stock market actually did a little bit worse. Okay? So it started off at 0.65, and now it's back down to 0.63. All right, so it didn't do quite as well. All right, let's do the same thing looking at what happens with Uncle Bill. So the first regression there, autoregression, and again, it's strongly autocorrelated. Durbin-Watson statistic is 0.018. And notice the slope with respect to day. Remember, under Reagan, the stock market increased by 0.64 per day. Under Bill Clinton, it increased 3.18 per day. So Uncle Bill Clinton was damn good if you were invested in the stock market, because you were making some money. All right? But it is autocorrelated. Look at what happens to those autocorrelations. Again, just like before, they get smaller and smaller. Let's look at what happens when we remove those 30 lags. The Durbin-Watson statistic is 1.94, so it's almost 2. And now what happens to the slope? The slope is now 3.04, so it also is a little bit worse once we remove the autocorrelations. But the point is, it still increased significantly better than it did under Reagan. You guys obviously weren't alive in those days, but you know that in presidential politics, Republicans always take credit for how great the economy does. Historically, the stock market always does better under a Democrat than it does under a Republican. If you look at what's happened to the stock market with Trump compared to Obama, you actually discover that the slope of increase was better under Obama than it was under Trump. I'm not telling you the goodness or badness of one party or another. I'm just pointing out that perception is not necessarily reality. And of course, the other thing is the stock market really a good measure of what's happening in the economy? Well, it's a part of the economy, but it's not the whole economy. All right. Let's talk about canonical discriminant analysis. Oh, so that spline and autocorrelation, what you can do is you can now put those two regressions together into one, and you can insert the spline, so make the spline as part of your regression model and run what we just did there a single time. And then include the autocorrelated error terms, and then number one, if you're comparing one president with another, you'll determine if there was a significant change in performance of the stock market, and so on, right? And you'll get a better idea of what's going on because you've removed the autocorrelated effects. All right. Let's talk about canonical discriminant analysis. All right, what we did last time was a principal components analysis. And as an example, we used a lizard morphology data set. And remember what was happening in a PCA. We were taking this coordinate system and we were shifting it and rotating it. Okay? And what we were accomplishing by doing that was discovering where the variation in the data set is. Oftentimes, you'll have a system in which you're looking at a number of different species. I don't know if any of you remember Lacey Dolan. She was a master's student here a number of years ago. Her master's thesis was on the morphology of foxes. She was comparing all these different species of foxes. Since then, she started working on bears. She's been working on black bears, polar bears, and grizzly bears. And she's done all of these sorts of morphological analyses. And if you look at her data, she starts off with a principal components analysis. There are the black bears, there are the grizzly bears, and there are the polar bears. Okay? And what you get when you look at something like this, oh yeah, man, there are differences between those groups. But principal components analysis is not a statistical test. It's not something that's designed to tell you if the groups are different. Now you can go ahead and construct your 95% confidence ellipses. If those ellipses don't overlap, that's fine, right? Then you might make the argument that they are different. But more often than not, what you'll discover is something that looks like this. Here are the polar bears, here are the grizzly bears, and there are the black bears. And a lot of people will look at that and throw up their hands and say, well, I guess there is no difference between those groups. But that's not fair, because this is not a statistical test. This is not asking the question, are they different? This is simply showing you where the variation is. So what we want to do now is figure out a way to decide if these three groups are different. Now, how would you approach something like that? Well, I mean, you might do the principal components analysis, get the scores, right? And then do the t-test on the scores, but of course, if they're overlapping like that, it's unlikely that you're going to find those differences. Well, the motivation behind the approach that we're going to use comes from politics. And it actually goes all the way back to British politics back in the early 1900s. And I don't know if you're familiar with British politics, but there's the Labour Party, and then there's the Conservative Party, the Tories, right? So they have fundamentally different value systems, just like in our country, right? We have the Republicans and the Democrats. And they have different values. I mean, everybody wants the country to do well and be successful and all of that sort of stuff, but they had different ideas about how to get to that particular point. Well, in British politics, it's not only the Tories and the Labours, there are also all these other little parties embedded in there as well. Well, back in the early 1900s, recall, well, even today, right, there's the House of Lords and the House of Commons. Okay? So who's in the House of Lords? Well, what does it sound like?
Wealthy.
Yeah, the Lords.
Yeah.
Right? And who are the members of the House of Lords? How do you get to be a member of the House of Lords? Just be rich? No. How do you get to be a member of the House of Lords? You have to be a lord. How do you become a lord? You have to be royalty, right? You have to be the landed gentry. So you get it by birth, right? It's a lordship, you get it by birth. Okay, it's something that's passed on in that parental lineage. The House of Commons is for the commoners. Now think about it. If you're in the House of Lords, what kind of person are you? I mean, aside from being snobby, what kind of person are you? A person with wealth, a person of leisure, all that sort of. Does that necessarily mean that you're conservative? Not necessarily. Does it necessarily mean that you're liberal? Not necessarily, right? On the other hand, somebody who's a commoner, it's probably much easier to decide or to figure out if this person is liberal or, you know, pro-union or pro-business or something of that sort. So the problem came in looking at members of the House of Lords and trying to figure out what their particular political beliefs were, what their basic fundamental value system was. So what these early statisticians did was they developed these questionnaires trying to figure out, right, all the ways that these people had voted on specific issues. So maybe there's an issue about taxes, so they say, you know, how they voted. And then there's an issue on welfare and how they voted. And then an issue on trade and how they voted, and so on. And in each of these things, there's a way that you would say, all right, this person wants to cut taxes, and this person wants to support unions, and this person wants to do this and that and the other thing. You can look at all of these votes and say, well, that's a typical liberal position, or that's a typical conservative position. All right? So what they did then is this. They plotted all of those data. And I'm drawing it out just in 2 dimensions. Obviously, if they're looking at 15 different variables, there are going to be 15 dimensions. So they have a bunch of data points. And there's a certain amount of variability, right? Just like if you talk to people today, if you talk to people that voted for Joe Biden, you'll find people that have a positive view about this and a negative view about that and so on. And the same thing as people that vote for Trump, right? So let's imagine here are the other group. And you notice there's some overlap between the two groups. So we've got certain, and I know my artwork is awful, but you can see there's some overlap between the two groups. The question is, we're asking the question, are these two groups different? How can we do that? I wish I had a different color. How could we do it? What approach should we take?
Find the average location on the X and Y for each group.
Yeah, that would be one start. So you find the average of all the little dots, and it's a point right there. And you find the average for all of the triangles. And it's a point right there. I'll fill it in. How's that? Great. Now what? I'll give you a hint. The name of the procedure is Canonical Discriminant Analysis. What does discriminant mean? To discriminate, right? To discriminate, but to tell the difference between two things. What does canonical mean? How many people here are Catholics? Anybody?
I was raised Catholic.
You were raised Catholic? So what? So I was raised a wannabe Catholic or an anti-Catholic. So when I went to parochial school, and we learned that all the Catholics were going straight to hell because they prayed to the Virgin Mary instead of directly to Jesus. That's what we learned. So you're damned. So, but the Lutherans and the Catholics have a catechism, right? And in the catechism are the canons. What are the canons? That's what I love about being in Southeast Missouri, where everybody is so hyper-religious. It doesn't make any difference what class I'm in, right? Don't ask students. These are people that come from solid, rock-solid religious families, and you ask them, okay, what's this? And they have no idea. The canons are the rules, okay? So I want a discriminant analysis based on rules. So what's the rule going to be? In other words, I'm going to have a very specific set of rules for doing this. There's another procedure that we will talk about, and I will show you how to do in R, called canonical correlation analysis. So it's going to be a correlation analysis based on rules. In canonical correlation analysis, it's not a discriminant analysis. What you do is you have two data sets. So you have a data set on water quality. And you have another data set on the fish. All these measurements you made on fish. So you do a principal components analysis on the water quality. And then you do a principal components analysis on the fish data. And then you ask the question, how are they related? So you do a canonical correlation, looking at the correlation between the fish variables and the water variables. And what you discover is that, hey, when the water has these qualities, you get these fish, that sort of thing. Back to the task at hand. How to do this? Well, I can kind of see, right? There's those things. Well, I missed one up there, okay? But I have these two basic groups. Remember, this is drawn in 2 dimensions, but in reality, I might have 15 dimensions here. So it's not. So what I'm asking the system to do is to draw a discriminating function between those 2 groups. And that function is going to look something like this. Now what I'm going to do is I'm going to draw a perpendicular line to that that looks like that. And I'm going to say that anything that's over here is going to be in this group, and anything that's over here is going to be in the other group. I still have overlap between the 2 groups. So the question is, although that's in 2 dimensions, if I have 5 dimensions, I might be able to draw, it's not going to be a discriminating line, it's going to be a discriminating plane or a hyperplane or something like that, okay? But I might be able to get perfect separation between the 2 groups. But at any rate, even on these 2 dimensions, most of the time, I'm right, okay? Some of the time, I'm not. This one really belongs over there. That one really belongs over there. This one really belongs over there, and so on. Okay? But I can now frame it in a statistical way. What's the probability, right, that I'm right if I draw the line right there? So I can affix to this thing a probability statement. What I want is I want to be right 95% of the time. Well, let's think about some ways that we can, I mean, the whole reason for doing this thing was, initially, when these statisticians were doing that, what they created this discriminant function, and they said, all right, anybody that's over here is a Tory, and everyone that's over here is a Laborite. So they were using that function to classify people. So if you ever applied for government assistance or for a loan or anything like that, or auto insurance, okay? You apply for auto insurance, how do they figure out how much they're going to charge you?
Like an interest? Or what do you mean?
Like,
No, I mean, when you buy auto insurance, right? You need insurance so you can drive your car. They're going to charge you a certain amount.
It's what you drive and age usually.
Yeah, it's going to be based on your age. It's going to be based on your past history of driving, how many tickets you've had, all that. All of that stuff goes into a discriminant function, a canonical discriminant function, that they've derived to say, okay, the people that are on this side are high risk, the people on this side are low risk. These people get one pay structure, these people get the other. And it's a little more complicated because they'll have 4 or 5 different discriminating functions, right? But they're going to classify you based on this kind of analysis. So,
Is there a way where you can look at each of the, each of those, I'm trying to think what they'd be, the principal components, take the error value from the mean, and then add them together and figure out a,
yeah, so what you're doing, so these are not principal components anymore.
Okay.
These are vectors, however.
all right.
And you can look at the score of each point on each vector.
Mhm.
So you get the XY coordinates,
Yeah.
okay? And that's how you're going to classify them based on which side
Yeah.
they're on.
Okay.
So how valuable is it as a tool? Going back to the bears, when you do the principal components analysis, you have something that looks like that. When you do the canonical discriminant analysis, you end up with that. It's different. Here, you're simply asking, where's the variation? Here you're asking, how are they different? Those are two different questions. One is, where is the variation? The next one is, how are they different? Okay? So you can tell right off the bat, oh, this is called canonical axis 1. This is called canonical axis 2. Those two guys, brown bear and grizzly bear, polar bear, those two differ along that axis. So canonical axis 1 discriminates between black bears and grizzly bears and polar bears. Canonical axis 2 discriminates between grizzlies and browns. All right, what is canonical axis 1? When you do a canonical discriminant analysis, just as in principal components analysis, you get a little table. It's going to say can 1, can 2. And then it's going to have all of your original variables. So your original variables are x1, x2, x3, x4, x5, all the way to x20 or whatever it is that you're using. And here it's going to give you the correlation between that axis and that variable. 0.9, 0.01, 0.02, 0.03, 0.76, 0.04, 0.02, 0.83, something like that. Now you go, oh, canonical axis 1 is defined by variable x1, variable x5, and variable x20. Canonical axis 2 is going to be fundamentally different. This is going to be 0, 0, this might be 0.9, 0, 0, 0, 0.7, 0, 0, all the way to the end. These two things are not necessarily orthogonal. Okay? In a canonical discriminant analysis, they are not necessarily orthogonal, but they are going to be fundamentally different. The first one is going to be associated with the bulk of the variance in the data. The second one will be associated with less. The first one is almost invariably significant. The second one, perhaps not. Okay? If you have 20 variables, you can have 20 canonical discriminant functions. By the time you get out to the 20th one, guaranteed, you will have found you've been uniquely divided every group. But that's silly, right? That's like saying, I have 2 data points, and I want to draw the regression line between those 2 data points. How good can I make the fit? What's the R square going to be? The R square is going to be 1. I have 2 data points. I can fit that line perfectly. The R square will be 1. If I have 20 variables, I can get damn close to getting almost perfect discrimination between my 20 groups. Okay? Depending on how noisy the data are. So, in a canonical discriminant, there are multiple ways to do canonical discriminant analysis. It is a statistical test. You're not going to get, right? You're not going to get the statistic that you're using is not going to be an F statistic. It's going to be a T statistic, but not the small t statistic. It's going to be a capital T statistic. So it's a T squared statistic, and it's capitalized. And all that means is we're using the basic T idea, right, to develop this statistical test. we're going to look at a difference, we're going to look at the divided by the standard error of the difference, and so on. Usually the statistical test that ends up being considered is Hotelling's trace, which is this capital T squared. So Hotelling's trace, or Wilkes lambda. Those are the two test statistics that are used most of the time, okay? With preference generally going towards Wilkes lambda. That's the one that you see reported in the literature most of the time. And when you do it, you're going to get a p-value that's associated with that statistic. All right. Now, let's imagine you have a relatively small data set. Let's imagine you've measured 100 variables on your bear skulls. So you've got x1, x2, all the way to x100. You've got 3 groups of bears, and you're trying to discriminate between them. You've got 40 grizzlies, 20 black bears, and 15 polar bears. What's the problem? Well, 60, I have 75 observations in 3 groups. I've got 100 variables. Can I find the difference between them? Guaranteed. I've got 100 different ways to look at it to find the difference between my 3 groups. I can do it each and every time. Will it be meaningful? Absolutely not. It's junk. Okay? There are 4 students in this class. I only need 3 things to distinguish between these 4 students. Okay? First thing, sex. All right, you're out. Okay, Bethany's out. Next thing, height. Okay? Next thing, weight. I further discriminated. So those 3 things, and I perfectly discriminated amongst 4. So with 100, I can easily discriminate amongst my 75 observations. But that's no good. That's meaningless. So what approach should I take? So you're sampling fish. You're in the river, you're in a big river, you're in the side channel, you're in some slough, you're in some small lake or something like that. You're looking at all these different, you have all these different species, and you're looking at all these different measurements on these fish. You're trying to discriminate between maybe you're working on one particular species of fish that is in all 5 of those different habitats. And you're trying to discriminate morphologically between your fish on the basis of habitat. Okay? You're asking the question, is this species of fish morphologically different in these different habitats? And your gut tells you they are. Because you've been out on the river and those fish are monsters. And you've been in that little backwater and they're just these tiny little things. Okay? So now you're trying to, and you've got 75 fish and you've got 100 variables that you're looking at. And it's meaningless. But yet, you've invested all this time and all this effort into doing this, and you'd like to discriminate. So what to do?
Maybe just use the 75 that are going to give you the best result.
All right, but 75, we're back to that thing, I can perfectly fit that line.
Oh, yeah.
Do you, when you write this paper, do you want to talk about 100 different variables? I sure as hell don't.
Oh, yeah, that's all.
And the person that's reading the paper certainly doesn't want to read about all 100. The person that's reading the paper just wants to know what's the key variable, what's the real difference. It might be 1 or 2 or 3 variables. So how to approach this? The solution is to use something that's called stepwise discriminant functions. It too is canonical, but now we're going to do it in a stepwise fashion. So the way we do it is we look at our groups and we search through all the variables and we find the one variable that gives us the best discrimination amongst our groups. And after we've got that one, we're going to look at all the remaining variables and find the next variable that we can add to the system that is going to give us good discrimination. Now, maybe the first variable divides our fish into 2 groups. And the second one divides them further, and the third one now divides all 5 groups. And from this point on, none of the new variables are going to add any information to our ability to discriminate, so we can stop. So we can keep adding variables until no further discrimination is possible or no further discrimination is necessary. That's called stepwise discriminant analysis. And the beauty of that particular approach is that it gives you a parsimonious model. Okay? What I mean by parsimonious is the simplest possible model that gives you the best discrimination amongst all of the groups. So now, how are you going to evaluate the discrimination that you get? Well, you can do it graphically, right? But there is another way to evaluate the model. And you do that by looking at something called the confusion matrix. And that's what the politicians, that's what the statisticians did with the British political system back in the early 1900s. So they took a person, or they took they have this discriminant function. Let's imagine, let me use a different example. One of the things that I've worked on over decades is identifying bats based on their vocalizations, based on their ultrasonic calls. So I get all of these calls, and I use canonical discriminant analysis to divide, because I don't know what they are. I just get all of these calls, and I run this analysis, and I'm able to say this is the maximum frequency, minimum frequency, slope of the call, all that sort of stuff, time between calls. I get all these variables that I can assign to each call that I'm getting for all these bats. But I'm not seeing the bats. All I have is their calls. So I take all of these calls and I now use my canonical discriminant analysis to divide them into groups. All right? So now I have all of these different groups of bats. And I could make my graph, and I see all of these circles. All right, there's one species, there's the other, there's the other, there's the other. And I'm going to arbitrarily assign names to those groups. A, B, C, D. And then I can look at something called the confusion matrix. So some members of A are out there, right? Some members of B are out here, right? There is some confusion amongst these. But in the confusion matrix, I do this: A, B, C, D, A, B, C, D, like this. Okay? How often did I take a species from A and classify it as A? Maybe 90% of the time. And 5% of the time it was classified as B, and 5% of the time it was classified as C, and 0% of the time it was classified as D. Maybe B gets classified as B 100% of the time. 0, 0, 0. C, maybe 0.1 there, maybe 0.1 there, maybe 0.8 there, and 0 there. And D, 0 there, 0.2 there, 0 there, and 0.8 there. So this shows me how much confusion I have in the system. That right there gives me an indicator of how good my discriminant function is in identifying my species. If it were perfect, species A would always be classified as species A. Species B would always be classified as species B, and so on. But they're not. So how do I get to the confusion matrix? Here's what I do. The University of New Mexico has a call library. So they have bat calls that are identified. We know exactly which species of bat produced that call. So I do the discriminant function analysis on the known bat calls. I now have a known quantity. And I use that discriminant analysis to test my new calls. So I have my known calls. I use the discriminant function as a classifier, and I use it to classify my new calls. And then I get my confusion matrix. Because I know what those things are. Now I'm taking all of my calls and I'm classifying them in this way. And here I have a group called A, and lo and behold, 90% of the time it gets classified as this species. 5% of the time it gets classified as that species. 5% of the time it gets classified as that species. In other words, I can build the discriminant function if I have knowns. I can build the discriminant function and then use the discriminant function to classify my unknowns. Well, when would that be useful? Well, it's useful when I'm doing these bat surveys. When else would it be useful? If you're going through the fossil record, you're finding skulls, and you're going, the hell is that thing? You take your measurements, you have all these known species and whatnot that you've already identified, and you simply use your known discriminant function to classify your unknown. Law enforcement uses that technique all the time. The FBI uses that technique all the time. Okay? So you can use canonical discriminant analysis to classify unknowns. I will give you an example of how that's done. I will show you how it's done in SAS, and I can do canonical discriminant analysis in R. I've just not yet figured out how to do it in a way that I can classify observations, but I know it's possible to do. So I'll work that up for you, and I will have that in a lecture for you over the next week or two. Let's see, we don't meet next week because of Thanksgiving. The following week, we have one more lecture that's online. All right, so that'll be an online lecture. I will post the canonical discriminant analysis and the stuff that's still outstanding, the autocorrelation lecture. I will post that. Before then, next week, look for the lecture on applying canonical discriminant analysis, and then there will be a few other bits of candy in there as well. Okay. And then we'll call it a semester. There will be a couple of homework assignments yet, and that'll be it. All right? Good deal. Easy.